Let's talk now about anonymous functions, or what are called lambdas. Anonymous functions are a primitive form that applies arguments to a function body as follows. So this would be a function that takes in two inputs. We designate the inputs by using the name slot, right? So slot is also another primitive that is tied with function, right? So we input slot 1 and slot 2, and we just sum something very simple. We just sum the two inputs. So if I press Shift Enter, I get this object that is the anonymous function. If I take this whole thing and use it as a head of an MX expression where I feed, in the arguments, I feed the values for the slots. Let's say I say 3 and 4, right? This applies the function. This takes this function defined here anonymously and applies it to 3 and 4, right? So I get 7. This construct implements what's called a lambda. It's a construct for functional programming. Essentially, we are here defining a pure function, a function that takes certain inputs and always spits out the same output from those inputs. This is the full form. However, the common syntactic sugar for this is to type it this way. So for every slot, I use the hash. And if I have more than one slot, I number those slots. So I have hash 1 plus hash 2, and then I use the ampersand to represent a function, right? So this is the sugared way of typing an anonymous function. And as you can see, this is more economic to type it that way. And then I can take this and I can apply it to, if I apply it to nothing, it spits an error. If I apply it to one parameter or one argument, again, spits an error. It says slot number 2 unoccupied. If I apply it to two parameters, I get the sum. I could apply it to more, but then it will ignore the rest. Furthermore, I can do this. I can take this anonymous function and bind it to a symbol. So I can say f equals this anonymous function, right? So here what I'm doing is here I'm doing some sort of combination. I'm combining a bunch of primitives into like a higher order primitive called a function, and then I'm able to use it. So once f here, actually let me check. So this function goes into the own values of f, because on the left hand side there is no MX expression, so this goes on the own values, right? So if I do own values f, I get the anonymous function. If I do down values f, I get nothing. And now that I bound this function to f, instead of doing this, what I can do is I can say now f for 4. What this does when Mathematica evaluates this, remember I said Mathematica evaluates in applicative order, so it starts by evaluating f. It looks for what f evaluates to in its own values, ben. So it evaluates this to the anonymous function, and then it evaluates the rest of that thing. And I get 4 plus 4 equals 8. One thing I should add is that when you define the function in this way, whatever you put in the body of the function does not get evaluated until you apply inputs to the function to get the results. Meaning that if I define f some other way, if I define f as slot 1 plus slot 2 plus 5 plus 6, right? F now equals this thing. Notice that 5 was not added to the 6. 5 was not added to the 6 because in the body of the function, whatever is in the body of the function does not get evaluated until we use the function, right? Everything inside the body is frozen. So if I now say f 0, 0, I get 5 plus 6. 5 plus 6 is already evaluated once the function is applied. So anonymous functions are one of the pillars of the functional design paradigm that Mathematica is designed around. The other pillar is what's called pattern matching. And this is a major one as far as Mathematica is concerned. It's like the core concept actually that gives Mathematica its power. The idea is that previously we would match exact M expressions, but that's sort of limited. So let's say I match X, Z, W. Let me first clear the everything. Clear the X, clear the Z, clear the W, right? So previously I would match, let's say this with bind it to 3, right? Or bind 3 to this M expression. So the idea here is I am matching with this whole M expression, right? So if I put in X, Z, W, I get back 3. If I change anything, I get the same expression. What if I wanted behavior such that I wanna transform this into 3, however, I don't care what's in this slot. I wanna compare against a pattern where some parts of the expression I don't care about. They could be anything, right? So what I could do is I could use the this symbol, right? This dash. This dash means anything can go here, any single thing, right? So if I say this equals 3, and now if I do X, Z, W, I get 3. If I do X, Z, 2, I get 3 because 2 is anything, right? If I put in a string, I get 3. However, if I change the Z to A, I don't, A has not been cleared, by the way. A had something in it, so let me clear the A too. Right, I get XA and then the string. So notice this pattern means that anything can go here, but the rest needs to be exact. This needs to be X, this needs to be Z, and so on and so forth. Right? So, and this dash needs to stand for a single thing. Like for example, if I have X, Z, and then let me put another expression here. Let's say Q, R, T, a sub-expression. Nothing happens. Oh, nothing happens because I made an error. I pressed Shift Enter here, so I erased this new definition. So let me press Shift Enter here, and now if I do this, yeah, I get 3. However, if I have something like this, I don't get anything because this dash cannot be equivalent to those two items, to those two M expressions in sequence. So this by itself is a sub-M expression. However, this with this is what's called a sequence. So whenever I have A, B, C, D, E, F, G, right? Those 3 together, let's say, or those 4 together are a sequence of sub-expressions. Right? So those cannot be represented by this dash. So the pattern does not fit. This only fits a single expression. Right? That's why this doesn't work. But if I remove the 6, it works. It matches with this. One way to test if an expression matches a pattern is to use the match Q primitive. Right, so there's the match Q primitive. This is a good way to test. So let's say I have this expression and I want to match it with this pattern. It says true. Why it says true? Why is it true? It's true because, yeah, this is a single expression, right? However, if I want to now match it with this pattern, It also says true because this expression matches this pattern. This is a single expression and QRT is a single expression. Now if I put in Y, let's say here, it doesn't match, it says false. So match Q is a good way to test when does your pattern match the expression or when it does not, right? And this does not match because this represents a single expression, while QRT comma Y is what's called a sequence. So yeah, so this gives us a more powerful way of defining those rules in the down values that we discussed previously. Instead of matching our expression to something really specific and concrete, we matched it to a pattern that allows us to transform a general variety of expressions rather than only transforming specific ones, right? And this sort of pattern matching is the second pillar of Mathematica that gives it its power, along with anonymous functions. And I would say, as far as Mathematica is concerned, compared with Lisp, for example, in Lisp, anonymous functions are the major pillar, while in Mathematica, I would say pattern matching is the major pillar of how Mathematica is designed and is to be used. Okay, the next place we can take this is thinking about what if we don't only want to recognize a pattern, we want to take whatever we match with. Let's say I have this pattern and I match this blank with something. I want to take whatever I match with here and use it on the right hand side, use it here. To do that, we have to use what's called labeled patterns. Say I have the symbol F, then here I made a mistake. I should have typed in clear F, not symbol F. And then I want to define a pattern to match against, which is F dash. And I want to set delay to, let's say, I want to take whatever this is, and I want to double it, let's say. Well, I have to name it first. The way I name it is I need to attach a symbol to the left of the dash. So I put in X, let's say. I can't put anything, but let me put X. This is not a symbol, by the way. The whole thing is not a symbol. This is a pattern that is named, that has a name X, right? And then I can put it on the right-hand side 2X. I need to clear F to make sure that I erase any history. So now if I use F with, let's say, 5, I get 10 with this, which is 5 times 2. So this is how you use labeled patterns. So we have encountered now two ways of defining so-called functions, or procedures. So say you define something like square. Well, square already exists in the namespace. It's a primitive. Mathematica already provides it. So if I do square 4, it gives me, I was expecting it to square the number. It does. I think this is something that's used in mathematical proofs or something. It's a symbol square. Anyway, Mathematica provides some kind of square function or procedure. I want to define my own. Let's say I see something in my code that says my square 5, and the intention is that it's going to square the number. There is no way for me to know what's it doing unless I look at its definition. So, what I wanted to say mainly is that we could come about the square function or procedure in two ways. We could define a rule. So I could say clear my square, right? And I want to define it using this pattern matching. I want to define a rule. So I would say my square, and I want to say match it with a pattern. And I want to name this pattern X. And I want to use that X on the now right-hand side. So I want to say X, and then caret 2, that's squared. By the way, for another form of syntactic sugar in the notebook, which is nice, You can type control caret and you get the subscript format. So I can just do square this way. This makes whatever you type in really similar to mathematical notation, which is nice, right? And this works, right? If I do my square 3, I will get 9. If I look at own values of my square, I see it's empty. If I look at down values of my square, I see the rule, the substitution rule or the rewrite rule. And there's one other useful primitive I can use, which is called definition. So I can say definition my square, and that will tell me, it's a down value. Anything that looks like this is a down value because it's telling me how my square would be rewritten if it was ahead of some kind of expression. All right. So those are the 3 ways to investigate what does my square look like: own values, down values, and definition. However, I could have defined my square in a different way, right? So instead of defining it as a pattern to match against with the rewrite rule, I could define it as an anonymous function. I could have said, I could have defined an anonymous function, anything control caret squared, right? So this is an anonymous function. If I run it by itself, this gives me an anonymous function. I can apply it to any input. It's going to give me 9. But however, I want to take this anonymous function and I want to bind it to a symbol. So I say my square equals this anonymous function. And that works too. And I can use my square 3 in the exact same way, and it spits out the same answer. There is no way by just looking at this to know whether my squared was defined using the anonymous function route or if it was defined using a pattern rule, right? Unless I look at the own values and the down values. So if I look at the own values, I see the pattern that takes my square and binds it to the anonymous function. So I know instantly this was defined using an anonymous function, and I see that the down values are empty. And then when I do a definition my square, I see that my square is just bound to an anonymous function. So those are 2 ways to do the same thing. Generally, if you look at the Mathematica documentation, they always recommend that you stick with the route or use the route of pattern rewriting or pattern matching and rewriting rules. However, both are provided and both are powerful. For some things, it might be more intuitive to use anonymous functions, and for others, it might be better to use rules. I wouldn't say use that all the time or that all the time. Okay. But to be sure how things are defined, if you forget or you are looking at someone else's code, you can always look at the definition and the own values and the down values. The behavior is the same though. Now I want to talk a bit about the role and meaning of the head of an expression. Notice I have been careful about calling a head of an expression a function or a procedure, although sometimes I do slip. Truth be told, heads can be considered to serve 2 purposes. Sometimes, yes, they can be taken to represent a procedure we define, like, for example, the my square I defined above. But also they might be a tag or a way of communicating what type of expression this is. For example, we might have 2 numbers representing the coordinates of a point on a plane, which we can represent with an expression as follows: point 3.3, comma 5.7. So that would represent a point in a plane. In this case, the head of this expression, I'm using it to kind of indicate some sort of type of what this expression is, rather than in my head representing a function or a procedure. The point I'm making is this. Mathematica is essentially a symbolic language. The expressions are expressions of symbols. There is no meaning attached to the symbols where you say, oh, this is a function or this is a type. You make up the meaning. You attach the meaning in your head to what those symbols mean, depending on the needs of what you are programming. However, Mathematica gives you complete freedom to attach any meaning you want. Sometimes a symbol for your purposes might represent a type. Sometimes a symbol for your purposes might represent a function. That's why you will notice I've been very hesitant in calling the built-in symbols from Mathematica functions. I would try sometimes to call them heads. I would just say this is a defined head or a primitive head. Either way, I mean, doesn't matter much. If I slip and I say sometimes function, you understand what I mean. You should understand what I mean. It's not, there's not like there's a function construct. It's all symbols. Well, except of course anonymous functions. Those are pure functions. Those were probably introduced to match what exists in Lisp and other functional languages. So they serve that purpose, but those are genuine pure functions. To emphasize this thing about the head sometimes representing a type, there's a useful primitive Mathematica provides called head. So let's say I apply head to point 3.3, 5.7, I get back the head of the expression. It's sometimes useful in some applications where you need to know what the head of the expression is to make a decision on how to proceed. So this is useful for that. What's interesting is that if you apply it to a primitive, let's say I apply it to a number, 6, let's say, I get integer. If I apply it to a floating point number, 5.3, I get real, right? It is as if internally the integer is an expression and has a head integer. So it's as if it's integer 6. It's as if it's represented like that, and it's an expression. Well, not really, I mean, but it is as if it's like that. If I type in integer 6, nothing will happen. So that's why when I deal with primitives, if I try to get the head of a primitive, I get what represents the type of that primitive. What if I go further? So I did head 6 and I got integer. Well, what if I did head integer? I get symbol. What if I do head of symbol? What is the type of symbol? It's symbol. So it's recursive. It's like symbols all the way down. It seems as if the symbol is the root type, right? So all the expressions have heads, which are the actual heads of the expressions. The primitives, when you apply head to them, give you their type. And then all those types are also symbols. If you keep applying head, you end up with symbol. It's as if symbol is the root of everything. And this emphasizes that Mathematica is a symbolic programming language at its core. Let's try this. Let me try to do head 5 times 4 plus 6 times 7. I press enter, I get integer. Why do I get integer? Because this evaluates to an integer. And then I do the head of that, I get symbol. I do the head of that, I get symbol. Doesn't matter how much I repeat applying the head, I always get symbol. So symbol is the root type, so to speak. Mathematica is not a typed language, as I said, as I repeat. At its core, it's a symbolic language. Now we can use heads as guards. What do I mean by guards? Well, patterns can be specified further to only match with expressions with certain heads. For example, in the my square that I defined above, I could define it so that it only works with integers, like so. So here I'm adding a guard to the pattern. So this is the pattern, the dash, and to its left is what I'm naming it. I'm naming it X, and to its right is the condition for accepting this pattern or matching to this pattern. What this is saying is that any expression that looks like this, my square bracket something, for me to match with it, this something needs to be an integer. So if I apply this, my square, let's say I apply it to 4, I get 16 as expected. But if I apply it to 4.0, which is not an integer, it's a real number, I get nothing. I get just the same expression given back to me. It evaluates to itself. If I do a string, I get this. Only if I put in an integer do I get matched with this expression, and I rewrite it, and Mathematica rewrites it to the right-hand side, which is the square. If I didn't have this, everything would have been squared. So 7 would have been squared, 7.0 would have been squared, even a string would have been squared. So if I say hello, I would have gotten hello squared, whatever that means. If I put in a symbol, y, let me clear the symbol first to make sure it's not defined upstream. I get y squared. But if I put in the guard, I say only match with integers, essentially. This won't work, and I'll get my squared y. This is really useful and helpful if you want to define transformations that only apply for certain strict inputs. That's not the only way of applying guards. There's another way of applying guards to an expression I'm trying to match against. We could also apply guards as predicates. What do I mean by predicates? I mean by a predicate, a function, some sort of function that returns true or false. True and false are primitives in Mathematica. So if I type in true, I get back true. If I type in false, I get back false. So I can use a function that returns true or false as a predicate that I can use as a guard. So how does that work? Well, let me show you. First, I clear my square to redefine it. Then I say my square. And here to use a predicate, I use the question mark sign. Now, after the question mark sign, I need to give a function. I need to place a function here. I could go two routes. I could either place either define a function before as a rewrite rule. So I want to define something simple, a simple predicate here. It has to be a function that returns true and false, true or false. So I want to keep it simple. I want to define something straightforward. I want to define something that will square if I feed it 3, and otherwise it will do nothing. It might seem useless, but this is a demonstrative example. So let me define a function called is3 pattern, and then what this does, it checks if x equals 3. This is how I check with for equality. I use the syntactic sugar of the double equal. This translates into some sort of M expression. You can use full form to check what it is. But what it does is that if x equals 3, it gives me back true. If x doesn't equal 3, it gives me back false. Now that I've defined this, I can use it as a guard. So to the right of the dash, I put a question mark, and then I say is 3. And then I say x squared. And now when I try my square function, let's say I give it 4, nothing happens. I give it a string, nothing happens. I give it another number, let me give it 5, nothing happens, because it doesn't, the guard doesn't give me true here. If I give it 3, however, something happens, it squares the 3. So this is one way of applying the predicate. There's another way. I didn't need to define this function separately. I could have used an anonymous function. So in this case, what I would do is I would put parentheses, and then I would place my anonymous function in there. And that would look like this. That would look like put more parentheses and then put hash for anything equals 3 and then ampersand. Remember, this is how I define an anonymous function that takes in something and compares it to 3 and returns true or false. So this gives me the exact same thing, and if I apply it, I get 9. If I try it with 5, I get nothing. This is how guards with heads or predicate functions that return true and false and have one input. This is how guards with those two options work. And this gives you a lot of control. Now I want to talk about sequences and the double dash and the triple dash patterns. Sequences have the following form. As you can see, they evaluate to themselves. They look like just any regular M expression. However, they have this interesting property. If they are within any enclosing M expression, they unfold themselves and you end up with just the content of the sequence. So if I take this sequence and I say, let's say F 1, 5, 6, Z, T, and then I put in the sequence and then I say A, B, C, you will see that because the sequence M expression is within encompassing M expression, when it is evaluated inside such a form, it will unfold itself and we will get the contents of it inside the enclosing M expression. So you will end up with something like this. So you can see we have 1, 5, 6, Z, T, and then the contents of the sequence. This is behavior I believe is called unfolding. And the key thing about this is now you are able to, you should be able to match against the sequence, right? And the way we match against the sequence is by using the double dash and the triple dash forms. The double dash matches against any sequence with one or more elements. The triple dash matches with any sequence with 0 or more elements. It's possible to have a sequence with 0 elements, of course, as I can show now. This is a sequence, for example, with 0 elements. So I can have F, A, B, C, sequence with 0 elements, and then 1, 2, 3, 1, 2, 3, and I end up with this. So the sequence with 0 elements gets unfolded and into nothing, essentially. Right? Again, the usefulness of this is that I can now pattern match against sequences. And I'll show you what I mean now. But I need to clarify something first. When Mathematica pattern matches, it always mutates the expressions in ways such that it tries to match the expression to the pattern, right? So if it's trying to match an expression to a pattern and it can change the expression in ways that are equivalent, that will still match the pattern in some way, then it does that. For example, F 1, 2, 3, 4, 5, right? So this is an expression. Mathematica knows that 1, 2, and then sequence 3, 4, and then 5. Mathematica knows that this expression is exactly equivalent to this expression. So if it ever sees itself in a situation where it needs to mutate this expression into this expression so that it can match a pattern, it will do that. And it can do that because those two expressions are equivalent anyway. They equal each other in a way, right? So if I do press enter, those evaluate to the same thing, right? That is the point of sequences, is that you can represent the expression in a different form that is equivalent with the idea that it will match a specific pattern. So let's make one example. So I first clear F, then I want to match against F with the sequence. So I use the double dash. And I want to do something simple. Let me just take whatever I matched against and put it in a list. So that's what this is doing. Match against F and a sequence, and then just place that sequence in a list. What does this do? Well, if I apply it to 1, 2, 3, 5, Mathematica recognizes this whole thing as a sequence and then prints it out. Pretty simple. What if I do something a little bit more subtle? Let's say I want to match F with the sequence and then one element and then another element. What does this do? Well, let me try it. Aha, it gives me 1, 2. It gives me the first two elements as a sequence. What it did here is that Mathematica took this and recognized that it, what I'm telling it here is I want to match this F to a pattern where I'm separating the last two elements by themselves, and then I want to take the rest of the sequence and put it in a list. So it recognizes that it could rewrite F as sequence 1, 2, and then there are two last elements. It takes a little bit of imagining how things mutate to see how this fits into this. Should be easy enough to get a grip on it eventually, right? So it recognizes that, hey, ignore the last two elements, well, match against them, but then what I want to output is X, right? So that's why I get 1, 2 here. Let me try something else. What happens if I want to match F to a sequence and then a single element and then a sequence? Okay, here it gives me 1. Does this make sense? Yeah, this makes sense. See, here Mathematica has multiple options. Here what I'm telling Mathematica is match this to a pattern where I have some element and I have a sequence to the left of the element and a sequence to the right of the element. Mathematica has two options here. It could either pick 2 and then to the right of 2 is sequence 3, 4, and to the left of 2 is sequence 1, or it could pick 3 and to the left of 3 is sequence 1, 2, and to the right of 3 is sequence 4. So the point is that there will be multiple options of how to subdivide F in a way that matches this pattern, right? And all Mathematica has to do is pick one. You know, there is no tension of how to divide F in ways that match the pattern. All Mathematica has to do is find one match and then apply the rule to it. That would satisfy the pattern matching, right? It's not a problem that multiple forms of F match this, right? What Mathematica needs only to do is to find one form to match against it. Although picking 3 as the element Y and having 1, 2 as the sequence X and 4 as the sequence Z would match this pattern, it's fine that 2 was picked. And typically you will find when you experiment with those things that Mathematica tends to pick the first element from the left that satisfies this pattern. So it starts with 1 and it doesn't satisfy, then it moves to 2 and it can select that Y equals 2 and then X will satisfy and Z will satisfy this pattern, right? So, and that's why we get 1. 1 is X, right? If I change this so that I have two lists, I wanna have a list of lists. The first list is the pattern X, the second list is the pattern Z, and I press Shift Enter, Oh, I cleared everything. Okay, let me press this again. Oh, there's an error. What's the error? Let me clear F again. Oh, okay, there's this dash that I printed out, that I typed in somehow. Okay, right. So if I try this, Shift Enter, and press here Shift Enter, so you'll see that X pattern matched with 1 by itself, and then Z pattern matched with 3 and 4, and of course Y is 2. I could put Y here also. And you can see X is the pattern, X is the sequence 1, Z is the sequence 3, 4, and then Y is just 2, as you can see here. And this is how pattern matching with a sequence works. Now I want to discuss conditions. So conditions have to do with applying conditions to match a pattern. You might ask yourself, we've already done that. We have guards, right? Well, why do we need conditions? Well, guards have to do with applying a single test to a single pattern. So here we're applying it to a single dash. But what if we want to test something that has to do with multiple inputs in the pattern? Let's say I want to apply a test to both X and Y at the same time. I cannot do that with guards. With guards, I would have to apply it only to Y or only to X, or I need to apply two separate tests, one to Y and one to X. I cannot apply a test that somehow uses both X and Y. And here's where conditions come in. So conditions are when we need to apply a test that produces true or false to multiple slots in the pattern at once. And then based on that test, we decide whether to do the rule rewrite or not. Let's do an example. So I'm gonna do clear all F to start fresh. And let's say I have a function with two slots, X, Y, and I wanna do some test that depends on both X and Y. The way I do that is I use the sugar form slash semicolon. So this is a condition, this stands for a condition. And then I just put in the condition. Condition I could try is X larger than Y, let's say. And then I do the set delayed. What do I want to do if X is larger than Y? Well, I want to do X minus Y. And then if I want to test this, so let me put in 5, 10, for example. Nothing happens because it doesn't meet the condition. 5 is not larger than Y. Let me put in 2, 6. Again, nothing happens. Let me swap those numbers. 6, 2. Aha, now I meet the condition and I do the substitution. I do the term rewrite and I get 6 minus 2, which is 4. Just for curiosity, I want to show you what is the desugared form is. I haven't done that in a while, and I don't need to keep doing that all the time. I trust if you are curious, you would search for the desugared form yourself. So let's do that. Let me hold the expression and let me send that to full form using the postfix notation. And then you'll see this is the this is the full form. Let me remove the semicolon so that I don't get the compound expression. And this is it, set delayed. And then inside set delayed, there's a condition first. And that condition is essentially the greater xy. So x greater than y in desugared form looks like this. So this addition of the condition expression essentially sets things such that this rule rewrite is not matched unless this condition is met. And again, this is useful as something other than normal guards in that we are here combining two slots together. We are combining both the X slot and the Y slot in making the decision. And those are conditions. We will use them more when we go through examples. One other useful thing we can do is to extract parts of M expressions. What do I mean by that? Say we have an general M expression, let's say G, Y, X, W, Z, M, K, Y, R, something like that. And I could use the built-in primitive called part. So I could say part, and then I take this M expression. Well, let me actually bind this to some variable. Let me say A. Symbol A binds to this, right? So when I type A, I get this M expression. So I can say part A and then give it a number. I get G. So if I do part A0, 0, it always points to the head, right? Then I can do 1, and I get the next expression in the MX expression. So this number works as an index. So 0 is the head, and then 1 is the first expression, the first argument, 2 is the second argument, so on and so forth. The syntactic sugar for part, I don't need to type part all the time. The syntactic sugar for part is to press escape and then two double square brackets, and I get this symbol, and then I put in the number. Then escape, two double square brackets, right brackets, right, to close the symbol. And this is how I type in part in concise form. So this gives me the head again. 1 gives me Y. 2 gives me X. 3 gives me W, so on and so forth. 4 Z. And then 5 gives me the fifth argument. Now I can do something interesting here. I can now go a step down and explore this sub-expression. So if I put in comma 0, I get the head of this sub-expression, which is M. Then I put 1, I get K. Put 2, I get Y. Then I need to step up to go to 6 to get R. So this is very versatile and very useful, and in programming in Mathematica you use it all the time, and it allows you to traverse the expression tree and access all levels of an M expression. So this is the part function. Okay, so we already know enough programming elements in Mathematica to do really powerful stuff. So let's do a bunch of examples. I want to start with sort, so we will do our own sort function. And we already know enough to conveniently do the sort function in 2 lines of code. It won't be that complicated, and I'll show you how. I'm going to call it my sort because Mathematica already has a sort function, I believe. Yeah, it has a sort function. Let me look up the help for this function. Sort list, so it sorts the elements of list into canonical order. And you can see some examples here, either alphabetical order or numerical order. So let me do this. Let me build a function that sorts numbers. Let's simplify things. And I said we can do it in 2 lines. Well, let me show you how we can do it in 2 lines. So let me start with the rule, right? I want to do a substitution rule. Well, first let me start with clear all, my sort. And typically I want to sort a list. right? That's what I want to do. So I'll have a list in my pattern, and then I want to do this. So I'm going to start with a sequence, 3 dashes. That means the sequence could have 0 elements or more. And then Y, single element. And then Z, another pattern. And then W, single element. And then R, another pattern. Sorry, another sequence, right? So this is the form that I want to apply a rule to and substitute. I want something that's a list, and then I might have a sequence, and then an element, and then a sequence, and then an element, and then a sequence. So what this is really saying, if I have a form, and embedded in that form, I can separate 2 elements, Y and W, and they don't have to be next to each other. They might have sequences to their right and left. They might have sequences in the middle, which is the Z. Wherever they are situated, I want to do this test. I want to check if Y is larger than W. I want to check if Y is larger than W. If Y is larger than W, then I have to do something. This means that this is an unordered list or a non-sorted list. I'll rewrite my sort in this way. Okay, so it went to the second line because there was not enough space to fit on a single line, right? So what do I want to do? I want to simply swap. I want to keep the X sequence where it is, and I want to simply swap Y and W. That's what I want to do. I want to put them back in order. That's what I want to do. I want to put them in order. Okay. And that's my rewrite rule. So, so I have this form, and I rewrite it as this. And I swap W and Y. So if I discover that I have a form where Y is larger than W, I just swap them. I put my sort again on the right-hand side because I want to keep repeating the substitution. Remember, the evaluator in Mathematica is fixed point, meaning it will after it gets the right-hand side, it will go to the rule base again and check if it can do another substitution. So I keep my sort here because I want it to go back and keep doing this, right? So repeatedly. So I wanted to repeatedly look for 2 elements that are not ordered, and then order them correctly, and then do it again and again and again. Notice here that I'm doing something curious. I'm using the fixed point evaluator itself to do the looping action, the iteration action, the iterative action. I'm not building any for loop or while loop like I would do in another language. If you discover yourself in Mathematica having to revert to while loops, you're doing something wrong. It does give you the while loop construct, but you don't need it. You can always revert to the fixed point evaluator. So anyway, this will repeat. When will this end? Well, we will reach a point where this rule will not apply anymore because all the elements will be ordered already. So we will never have a condition where Y is larger than W. In that case, we want to do another rule. We want to step down to another rule, right? So the evaluator starts with this rule and keeps applying it. And then once it's done and it doesn't apply anymore, it moves to the second rule in the list. The second rule in the down values list. In this case, I want to take this pattern. Well, I don't need to take this pattern. I just take the whole list. It will be a list that looks like this. And I just want to output the list. So I just do this to output the list. And that's it. That's my sort function. That's my sort function in 2 lines of code, as I promised you. Okay, let's test it. The first step I need to do is I need to create a random array that's not ordered, and I want to see if I can order it. So I want to use a built-in function in Mathematica called range. What does that do for me? Well, let's say I want to build an array of 100 elements. So this will simply build an array and count from 1 to 100. But that's not really what I want. I want 100 random numbers. So what I could do is I could pass this array into the map function. The map function does this thing. So if you look at the help of the map function, by the way, in Mathematica notebooks, you go ahead to help by pressing function F1, right? And on the keyboard. So this is map. It applies a function to each element in the expression. The expression could be a compound expression, and one of the compound expressions is an array, right? So that's what it does. So I want to apply some sort of function that's going to take each element in this array and just spit out a random number. So what I could do is I could define an anonymous function. Let's say I want to output 5, just something random. So this is a function that takes in any number of inputs really and outputs constant 5. If I try that, all will be 5s, but that's also not what I want. I want something random. So there's another function, built-in function that I can use called random. I just need to give it the type of output I want from it, and then I need to give it a random number from what to what. So let's say I wanna output a random number from 1 to 100, so or 0 to 100. So I do this, and this is it. So this maps this function into this array, and this gives me this random array. I can put it in a variable, in a symbol, put a semicolon, and that's my random unorganized array. Right? There's an interesting function in Mathematica called bar chart that allows me to take an array and plot it as a bar chart essentially. So it looks something like this. Right. So this is element 1. Element 1 is 54, as you see, so on and so forth, and it's unordered as you can see here. And now I want to just sort it. So I do my sort. And magically it's sorted. Those 2 lines of code achieve the objective of sorting this array. Let me do then our bar chart. And you see the array is fully sorted from the smallest element up to the largest element at the end. Is 100 element array excessive? I don't think so. Can handle it clearly. All right. So this is one thing you can do if you wanna if you want to have the bar chart fill the whole document, fill the whole page width. So you could do image size property, and you can set it at full. This is what's called the rule, by the way, this syntactic sugar, this form of expression. We'll talk about it later. Right. And then here, image size full. And that's the sorted array. So it works. It works. those two lines of code. Now I want to do something even more interesting. I want to build an animation of the sort process. So what I want to do is I want to take my mysort function and I want to build another function called mysort steps. I want to capture all the steps of the sort process. So mysort steps, and then mysort steps, mysort steps, shift enter, right? So what do I mean capture all the steps of the process? I want to, so here it's doing an iteration. It's doing it's swapping two elements, and then it's continuing and swapping two elements until the set is ordered. I want to capture each step in a separate array. So what I want to do, or array or a list, I'm calling it array, I shouldn't, I should call it lists. Arrays are concepts from C, is a concept from C. Anyway, so because I want to capture it step by step, what I want to really get as an output is a list of lists, and each list in this big list should be like one step. Okay, so how can I do this? Well, what can I do? What I can do is that I need to consider that I have an input that's a list of lists, right? So it will look something like this, and it will have at least one list at the beginning, but it will have in front of that list anything essentially. So let me put in, what shall I put in? T 3 dashes, right? So I could either have a list of one list, so this T 3 dashes could be nothing, because when I have 3 dashes, it could be an empty sequence, or it could be a bunch of items, elements, right? And a bunch of lists essentially. And this would be, this format will tell me that this part here would be the last list in this list of lists. So what do I want to do with this last list? In this list of lists, I want to check, is y larger than w? If it is, I need to do the swap. So that's the same. But that swap, this swapped list, it needs to be padded to the end. So, so I need to copy this whole thing. I need to keep it as is. I need to keep t, keep x, y, z, w, r, right? And then pad to the end the swapped, the list with the swapped items. Because y is larger than w, I need to swap w and y. That's what I'm doing, right? So I'm feeding this function a list of lists, and then it looks at the last item in this list of lists and checks if it needs to do a swap. And if it does need to do a swap, it copies the same list of lists again, and then it appends the it appends the list with the swapped elements at the end. And it keeps repeating this, keeps appending until we end up with a big list where each element is a list, and each step in the list shows you one step in the algorithm, right? And then at the end, when there's nothing more to order, I just spit out that list of lists. So so is this correct? So yeah, this should be correct. This should be correct. Well, I could do this actually. This will also work. Right, so this would be a list of lists, and then I'll just spit it out. Okay, so let's try this. So if I try this, my sort steps, and I feed it A. But remember now, A needs to be a list of lists. So I need to, A by itself is just a list. So I need to embed it inside a list. And I press Shift Enter. Takes a while to calculate, but it gives me some big thing. It doesn't even display it all. What I can do is I can save this into another symbol. And then what I can do now is I can explore the elements of this list of lists. So this is something big, but doesn't matter. I can use the part function. So I can explore the parts of this. B0 is list, that's the head. Then 1 is the first list. 2 is the second list. 3 is the third list. So this shows me how each step in the sorting process works. How does the list mutate as it moves from one step of the sorting process to the next? How many steps does it take it to sort it completely? Well, I can check the length of B. Okay, so this takes 1904 steps. Takes a while, but it does because I used a big list essentially. I used the list with 100 elements. Yeah. So there's something cool we can do in Mathematica. There's something called so if I do bar chart, I can do bar chart for one of those, each one of those lists. So I can do B1, let's say B1, and that will give me a bar chart for 1, and then I can do 2, and that will show me how the thing evolved. However, I can animate this. There's another function called manipulate. So I feed it bar chart, and instead of having a constant number, I put in an index here. Then I say take the index from 1 to the length of B, 1904, whatever that is, and oh, I need to provide the step. So from 1 to length of B in steps of 1. Right? And then I think I want to do image size full. Oh, can't I put image size here? Maybe image size is for bar charts. Okay. Full. And now this should give me an animation. This should take this bar chart, BI image size full. I is the knob that the manipulate works on, and it varies I from 1 to length B, and it allows me to step through each step, and for each step allows me to draw the bar chart. So if I do this, I end up with something like this. And if I press play, I get the animation. This is the sort function that we implemented in 2 lines, and we are animating right now. Isn't that cool? So you can see how Mathematica's concepts, it's like a steep learning curve. Like the concepts accumulate slowly, one by one tiny step, and then it suddenly explodes, and you suddenly at some point you suddenly start to get that there's a lot of interesting things you can do based on those seemingly simple concepts that you started with, right? So yeah, I don't know, I think this is cool, honestly, but I can slow it down even, right? But this is the sort function, right? So with that, I think I'm gonna end this video here, and we're gonna continue with more examples next time. Thank you for listening so far.